Um, we would like to comment on a number of issues that arise when we are trying to apply linear elastic fracture mechanics to different problems. So let's make some remarks on the use of LEFM. Remember, we're doing linear elastic fracture mechanics, which essentially addresses the fracture of brittle materials where there's little or no plasticity, and for that matter, any other inelastic process that is going on. So I should comment, and you can read supporting sections from your book, that if this assumption is not satisfied, there is still something you can do to predict fracture. Fracture is always an issue, but we are, as we've done in some other topics, we are trying to give you a glimpse of what is going on in the mechanics of materials beyond the level that we've considered in basic mechanics on materials, where we use uniaxial, essentially, stress-strain behavior. We're trying to give you a path through a relatively general landscape of mechanics on materials, and we're doing so by covering selected topics. So we are presently in a situation where we've done LEFM by making use of the following criterion, which is, remember, for mode 1. And I told you that, well, the idea remains the same, except that if we don't have mode 1, you just replace it by mode 2 or mode 3, whatever. So that's what I'd like to comment on further. And remember also that here, K is something that we know. It's going to be some form factor that depends on this value of alpha, which is a ratio of the crack size to a lateral dimension of the structure, multiplying the gross stress, which is always calculated at the cross section where the crack is present. We take the maximum value, but we do so by omitting the presence of the crack during the calculation, and then the rest is root pi a. So that's the idea. That's what we would like to have. In general, of course, we would like to replace this by some safety factor, of course, in order to predict some critical values, let's say, by some safety factor xk. Okay, so now let me now proceed a little bit further and comment on, as I said, a number of cases. The first case that we are going to look at is the following situation. So it's almost like one of our classical cases. So we have a plate. And it has a width B. The width is denoted as B because there's an edge crack of size A. Okay, and it will have a certain thickness as well, T. And we're going to load it. But as we load it, let's take the central axis. So that would be sort of the central plane. We're not going to load it through the center. We're going to load it with some offset. So that's where we are going to apply the load, and that offset is through some amount, let's say E. Now, what we've assumed intrinsically so far is that this load is applied right through the middle, so that the state of stress or the equivalent representation of this loading on the cross section where the crack is present is just loading. It will give rise to a uniform stress field, etc. if the crack is not there, of course. So, but however, if we do an offset, there will be some tensile force in addition to bending applied with respect to the central axis, or conversely stated, or just in another way stated, the stress field in the vicinity of the crack zone is not going to be uniform, or at the cross section where the crack is present, omitting the presence of the crack, it's not going to be uniform. There's going to be some bending stresses, so there's going to be some distribution of the stress, which is far from being a constant. So that's a case that looks slightly more complicated because it doesn't seem to be a scenario that we've actually looked at, but in fact it is a case that we have looked at. And the way we are going to address this scenario is by decomposing the problem into two individual parts. In the first part, we're going to take the same geometry. In fact, we're going to take the same geometry once again in the second part. So we have the crack and width B in all cases. Okay, thickness is T. And then we are going to consider the following two cases. Well, suppose there was no offset. Suppose the crack was loaded, the plate was loaded right through the middle through this amount P. That's the first scenario. The second scenario that we're going to look at is, again, we consider the center plane, and with respect to that plane, we impose a bending moment about the line that I have drawn, about that line. And that bending moment is something we know. It is equal to E times P. Now that bending moment, if the offset was in the other direction, it would also have an effect on the mechanics of fracture. But in this case, it certainly has an effect because it tries to open the crack. If it were in the other direction, it would try to close the crack. But ultimately, that itself doesn't mean that we can ignore it. We should eventually, you'll see, consider it in conjunction, in combination with the tensile stress itself. So in this case, it's opening mode. I don't need to worry about the crack closing. So this bending moment is certainly going to be relevant, and there is the same bending moment in the other direction as well. So now what I need is the value of K1 in this case. So K1 value. If I can calculate what the K1 value is, the criterion remains the same. I will compare it against the fracture toughness, possibly scaled by some safety factor, to decide if there is some critical situation or not. The problem is I don't know how to calculate K1 for this scenario, but I do know how to calculate it individually for that and that scenario. Well, in this particular case, let us call this K1, okay? Now, 1 not for the stress intensity, but rather this is situation 1, and this is situation 2. Or in fact, let's go ahead and just call this Kp and call this Km. So both are mode 1, and I know that in this case, Kp is equal to some form factor that is specific to this loading scenario, okay? And multiplying the gross stress that is specific to this loading, root pi a. And for pure bending, similarly, if I want to calculate the mode 1 stress intensity factor, there is a form factor, a function that is relevant to this case. Alpha in all cases is A over B. Then there will be a gross stress. Let me just indicate it by I'm dropping the notation G and putting SP or SM to indicate the difference, and root pi a. So I know individually what the stress intensity factors are. So if I had only this, I would compare that value against the fracture toughness, or if I had only that, I would compare that value against the fracture toughness. The problem is now that I have both of them, right? So, but let's continue further. Well, what is SP in this case? So first of all, SP, the maximum stress at the cross-section where the crack is present, omitting the presence of the crack. That's the way I should always remember. So it's force, in this case, divided by the area. So it's P over BT. Well, what's the gross stress in this case? Again, the same idea, maximum stress, tensile stress in this case here, at the cross-section where the crack is present, but I omitted. So it's MC over I, and we've calculated this before. It's going to be 6M over B squared T, okay? So, all right, good. So I know exactly what I am supposed to do. Let's also indicate what the values of alpha are, and here I will make a correction. Here the value of alpha is A over B. Here, let me correct, the value of alpha is given as not A over B, but rather as A over 2B. So if I've made a mistake in earlier slides, so please correct your notes at this stage. Okay, good. So individually, I know exactly what I'm supposed to do. The problem is I don't have either scenario, I have that scenario. Now, this is where some understanding of what K1 is associated with is important. Remember, and I'm going to write this with a blue pencil. So it's just a reminder. Let's concentrate eventually on the mode 1 stress intensity factor. But remember that ultimately we have, let's put it in parentheses like this, we know that the stress intensity factor is a quantity that appears in the calculation of the stress, and it is scaled through a factor root pi r, where I is the distance from the tip of the crack. So the stress field in the vicinity of the crack tip, let's say sigma y, has a factor like this multiplied by some orientation information that has to do with theta. Okay, so that's how the stress appears. R is a purely geometrical quantity. Everything about the loading is in K1. Okay, so now let me ask you a question. With that information in mind, right? Do you now have an idea about how I should calculate K1 for that scenario? Okay, so you can pause the video and think as long as you want, but now let me proceed and give you some more hints. Now, first of all, that's the stress field. There is similarly going to be a stress field that is associated with this scenario. It's going to be sigma p, okay, the stress field associated with that, and it's going to be root pi r, whatever. Let's put that also in parentheses. There's going to be a stress field that's probably going to be associated with that, root pi r. Okay. And now, if I were to ask you, well, I am interested in the stress field for that scenario, and I know the stress field for this and that scenario. In this scenario, the loading is equivalent to the sum of that plus that. So what is the stress field? If I ask you the question in this fashion, you would probably come up with the idea of superposition, because we're doing linear elasticity. And in linear elasticity, we know that if the geometry is the same, and you have a loading that is a combination of two loadings, the resulting stress field is a combination, and in fact, it's a sum of the two stress fields. So conceptually, this problem is a sum, conceptual sum of these two problems, and that problem, therefore, is going to be, as a result, a sum of these two problems. So what we should be summing is the stress field. The stress field is scaled by the same factor root pi r, if you like, and therefore, if I want to have a combined stress intensity factor, that should be simply a sum of Kp plus Km. So in other words, in this scenario, if I want to estimate the value of K1, it is equal to the value of Kp plus the value of Km. Okay. And this idea directly follows from the superposition principle in linear elasticity. Okay. What you have to notice is we are not taking some measure of gross stress and multiplying with, let's say, the sum of the form factors, or we're not summing the form factors and also summing the gross stresses multiplying by root pi a. No. So you have an individual form factor for each case, you have an individual value form, and eventually a numerical value for the gross stress. The root pi a is identical, yes, but otherwise it's not identical, right? So in other words, if you eventually look at this value, the value is fpsp plus fmsm sum root pi a. Okay, but this is not a nice way to memorize, I think. What we have to remember is the principle of superposition. You individually attack the problems, sum them, and then assess the criticality of the overall situation through still the same criterion. Okay, so that's the first remark that we would like to address, and this simple superposition criterion allows us to rapidly propagate beyond simple loadings that we have considered and look at really more complicated loadings, examples to which you can find in the book. Now, in the book, you can also find examples to many different types of geometries and many different types of loadings, as I said. Now, let me give you some example to the types of loadings that we can consider further. is a continuation of the same remark. So what we are going to do is we are going to consider a cylindrical geometry. So simultaneously, I'm going to use the principle of superposition and also comment on when you shouldn't use it. And we're going to see for the first time a different mode. So what we have in this case is a cylinder. Okay. And we're going to assume that there is a crack. Now, at this stage, maybe it's a good idea because we're drawing it for the first time. Let me emphasize the crack by exaggerating the extent of the separation of the surfaces. So that's how the crack looks. Okay. So now, the crack is associated with, right, these portions. And the central portion here, let's do that in a different color. This is the portion that is attached. So there we have material, but in the surrounding portion, right? In this portion, we have a crack. So the red portion is the crack surface. So it's not a through thickness crack, it's not rectangular, it's now a different geometry. So we are going to indicate the loading. We can have different types of loading. We can have a torque, we can have a bending moment, and we can have an axial load. And I'm assuming that we have the same thing on the other edge as well, on the other surface. Then we have the dimensions, of course. Now, we are going to indicate the half width of the crack with A. So that is this distance. This is A. Okay, edge crack A, edge crack A. Okay, and that runs through the circumference. And then the half width of the whole thing is, as usual, B. And in this case, it clearly corresponds to the radius of our cylinder. And now, let us think about the different types of modes that we can have. And in doing so, let me remind you that the moment of inertia of a disk or a circle, let's say, is equal to pi over 4 r to the power 4th, which is b to the 4th in this case, and j circle is just twice that, it's pi over 2b to the 4th. So we can keep those in mind because we will need them. So now, first of all, both the tensile load and the bending moment will try to open the crack on the side. Okay. So then there's obviously an opening mode, which I now know is mode 1. Okay, so therefore mode 1 is a sum. How do I calculate it? The mode 1 stress intensity factor has a contribution from the normal load and also from the bending moment. So the normal load will have its own form factor and will have its own gross stress. And the bending moment will have its own form factor and its own gross stress. They both multiply root pi a. And you can remember, so first of all, Fp, right? The value of alpha in both cases, it's equal to A over B, okay? But the functional form for these two can be different. In general, it is different, right? So I need to look up into the tables in the book to understand what they exactly look like. But I should remember, that's nothing to memorize, but what I should remember is how to calculate the gross stresses. Cross-section, at the cross-section where the crack is present, omitting the presence of the crack. So it's the load divided by the area of the cross-section, omitting the presence of the crack. So it's pi b squared. Okay, that's simple. Now, on the other hand, Sm is, again, it's going to come from mc over I because that is where C is B in this case. It's the maximum stress, tensile stress at the point where so at that location it's tensile, at the point where at the cross section where the crack is present, but omitting the presence of the crack. So the I value I'm going to use is that value, so because I omit the presence of the crack. So it's going to be, in this case, from mb over I, b is the radius, it's c, so it's 4m over pi b cubed, using that expression for I. Okay, so if you're concerned with mode 1, that's essentially what you need to do. Now, if that's all you have, in other words, P and M, this is all you need. And you can compare that against the value of K1C, okay, to within a safety factor perhaps. Now, alternatively, let us now concentrate on the scenario. This is one scenario. Another scenario is when there is only a torque, okay? And when there is only a torque, now it's a different mode. It's a mode where the surfaces actually sort of they don't exactly slip, they rotate with respect to one another. So we've discussed this example actually earlier when we were talking about different modes. So this is mode 3. So if I'm talking about only the case of the presence of the torque, I'm concerned with K3. How do I calculate K3? Well, there will be a form factor that is special to this geometry and loading. There will be a gross stress multiplying root pi a. Once I know that value, I will compare it against a fracture toughness that has to do with mode 3. So K3C, the critical stress intensity factor for mode 3. So the expression, notice, remains the same. The material, the parameter K3C is not the same as K1C. That's what we have to keep in mind. In different modes, materials fail in different fashions. Okay, so now the question is, well, what is the value of the gross stress? Well, the value of the gross stress is simply the same definition. The maximum stress at the cross-section where the crack is present, omitting the presence of the crack. So if I omit the presence of the crack, I simply have a circle, I have a torque on it. The maximum stress is a maximum shear stress, and the maximum value occurs at the rim of the geometry. So that's like TC over J, and C here is equal to the radius B. And if you use the expression for J, you will end up with 2T over pi B cubed. You see, the idea of how the gross stress should be calculated is still something that is relevant. And well, you might also ask yourself, well, where does this K3 appear? Well, this K3, just like the normal stresses, eventually appears in the expression for the stress distribution. In this case, the shear stress distribution, which is K3 scaled by root pi r, and some additional information that has to do with the orientation information from the crack tip. So the role of the stress intensity factor for mode 3 is the same as the role of K1 for mode 1. It gives us information. It appears as the parameter that has all the loading and material information, loading and crack geometry information within the expression for this relevant stress field. Now, finally, what we have to keep in mind is we can combine the same modes but not different modes. So in other words, if I have everything applied at the same time, how do I decide fracture? If I had only these, that's easy. If I had only that, that's also easy. Well, what if I have all of them? So shall I sum the stress intensity factors and compare it against, say, the sum of these? Well, I don't know if that makes sense. I certainly cannot sum these and compare it against that, or sum these compared against this, because these are different modes. These are normal stresses, these are shear stresses, so I cannot sum apples and oranges. I already have such an experience from failure criteria. If I have simultaneous application of the normal and the shear stresses, it's not so easy to decide on whether failure occurs or not. We have criteria, and for Mises criteria, fairly complicated looking one, which is one of them. What you have to do is combine in some clever fashion these individual contributions to the stress intensity from different modes, combine them in some clever fashion, and decide by also making use of the material strength in different modes to decide if failure occurs or not. And ultimately, if I eventually write a criterion, that criterion, unlike these two criteria, unlike the expressions for the stress intensity factors, which are very mathematical actually, they will be highly based on experience and eventually the material behavior. So to give you an idea about the existence of multiple modes at the same time, so let me give you a combined sort of, or it's called a mixed mode fracture situation, okay? So that's the second remark, therefore, that I would like to make in the context of this problem. So it's mixed mode fracture. Okay, so to demonstrate this idea, we will again take our usual plate, but you see, although the plate example is very easy, we can easily also, just as easily, enrich it beyond our existing level of proficiency. I'm going to assume that there is a crack, and that crack is much less than the half width. Looks like a standard scenario. There is a far field loading. The height, if you like, is very large compared to the width. Let's just denote it simply by S, of course, on both sides. So far, so good. If I put the crack like this, there is nothing fancy. It's our prototypical scenario, but I'm not going to put it like that. I'm going to put it at an angle. And all of a sudden, again, we are out of our, let's say, comfort zone. We don't know what to do with it, right? And the width of the crack is 2a. And I do know that it is at an angle of orientation theta. Okay. So, well, what do I do, right? Well, what you can do is, again, you can decompose this problem in some sense into two parts. What I know, and this is sort of an application of Morse circle, you can, at this point, right, at that point, you have a state of stress with respect to our convenient coordinate system, which is a normal stress in that direction. But if I choose a different coordinate system, or I'm looking at a rotated plane, which naturally aligns with the crack, there will be different components of the stress, which I can calculate from the Morse circle. In particular, in general, there will be a shear stress, and there will be a normal stress. Now, when I then rotate the picture locally, if I just concentrate on the normal stress, I will see a crack that is loaded in the normal direction. It's a plate through thickness crack. It's our prototypical scenario. And if I concentrate only on tau, I have a plate, but it is loaded in shear. Now, the tension case I've seen before. Shear, I haven't, but I know that it's a mode that I can consider. So first, let's take the case of mode 1. Mode 1 is equal to the gross stress that is associated with tension. In this case, it's sigma. That's the gross stress, multiplying root pi a. Here, I'm going to assume a is much less than 1. The form factor eventually is equal to 1, so I'm not putting any form factor there. Okay, so that's sigma. Now, there is also a mode 2. Now, it's mode 2. I've said this earlier before. So, for instance, torsion induces shear stress. And for torsion, we said that we have mode 3. That was the example that we just also considered. But just like bending is not also always mode 2, torsion or shear stresses is not always mode 3. In fact, in this case, it's mode 2 because shear will only make these surfaces, crack surfaces, slide with respect to each other perfectly, just like in our initial discussion of mode 2. The surfaces do not rotate with respect to one another, they just slide. So it's actually mode 2, and therefore the way I would calculate it is like this. But notice, one of them is a normal stress, the other one has to do with a shear stress. Okay, well, what are the values of sigma and tau? They come directly from the Morse circle. If you look at the expressions that you have, sigma is nothing but s cosine squared theta, and tau is nothing but s cosine theta sine theta. And it's something that I actually can calculate based on Morse circle or from the explicit equations that we wrote when we were considering stress at a point along planes, on planes that are oriented at different angles. Now, the problem that I am facing is that these two modes are not the same, and therefore I cannot combine them. So these are individually theoretical, but if I would like to decide whether failure occurs or not, ultimately, just like looking at multi-axial failure criteria, I have to do experiments. So, well, how can I do experiments? Well, what you can do is something simple that you can do is you can actually, just like we've sort of partially discussed, in the case of failure criteria, what I can do is experiments, very well controlled experiments. I have two parameters, a K1 and a K2. And I know that if this is, let's say, the K1 axis, I will scale it by K1C, the fracture knot toughness for mode 1. The maximum value, so suppose I'm loading the material, and suppose the crack is parallel, so theta is equal to 0, so there's only mode 1. So I will keep increasing the load until I reach a value of 1. At a value of 1, failure will occur. Okay? Now, alternatively, what I can do is I can look at a mode 2 type loading, pure mode 2. Suppose the crack is flat, but I put a tangential shear type loading, and in that case I will increase in this direction. I will increase the shear force until the value of K2 over K2C reaches a value of 1, and then failure will occur. Now the question is, well, what happens in combination? Now in combination it's easy to adjust. If I increase for a given load the value of theta, at theta equals 0, it's pure mode 1. If I keep increasing as I keep moving in that direction. But if I increase theta a little bit, it will be combined load. So there will be combined loading. There will be simultaneously K1 and K2 contributions associated with S. And therefore, on this plane, on this space of K1 and K2, I will be moving in a direction that is not horizontal, but it is at some angle. So I can move at a certain angle, and I can keep increasing S, which will proportionally increase sigma and tau, and therefore K1 and K2, and therefore I will move along a line until I hit some point where failure occurs. Let's say that's that point. Now in this fashion, I can do experiments associated with different directions. I can proportionally increase K1 and K2, and I can collect data. And suppose these points are points that have to do with failure. And then I go ahead and I try to fit a failure surface to these points. And now that failure surface may or may not look nice. If this is the data, perhaps I should draw something that goes nicely in through those points. But suppose I do as well as I can, and this is what I obtain. Now I might ask myself, well, is there a nice equation for this line? There might be. So for instance, it might be that this line, it almost looks like a circle that is scaled. I have not drawn it to exact proportion. This distance is less than that distance. So it might be a distorted circle. In reality, perhaps it's a circle. So why don't I model that line as a circle? How do I write the equation of a circle? Well, I would write x squared plus y squared is equal to 1. That would be the radius of the circle. So x in this case is K1 over K1C squared plus y squared, which is K2 over K2C, is equal to 1 is the failure surface. In general, I don't want failure. I want to be less than that value, the radius of the circle 1, or if it's equal, I am on the surface. That's the onset of failure, right? Okay, and if my design indicates that somehow I lie outside here, then it's not a good idea. My design is a bad design. So here what we have is a mixed mode fracture criterion. But that criterion is based on the green data that I collect. This is data, and this is my fit. We've seen the concept of fit now several times for failure surfaces associated with plasticity. We've seen it for the modeling of plasticity in the stress-strain curve itself, and now we're seeing it again. So this is experimental. And the extent to which this combined failure criteria is valid depends on the experimental data. So the experimental data, if it is, say, like that, perhaps I would like to do something different. Perhaps instead of 2, I would like to use an exponent alpha, say the same for both of them, and I'd like to choose a value that is able to replicate this line better. So if you choose, instead of an exponent 2, a higher value, you will see that this line will approach that line. You can try plotting x squared plus y squared, replace with x to the alpha plus y to the alpha equals 1. As you increase the alpha value of alpha, then the line that you draw will become, will move outwards. So for instance, you can choose it to be 4, but I don't know if that's a good idea. It depends on the data. If the data is lying here, then the blue line is a better choice. If the data is like this, the red line is a better choice. So it all depends on the data. But what I have written here, so it's for the red line, and so with an exponent of 2 is one combined or mixed mode fracture criterion that you can choose. So you calculate individually 2 modes and then combining them in this experimentally based equation to decide if there is fracture or not. So going back to the previous example, if we had the torsion of a cylinder with a circular crack, then there's a mode 1 contribution that is associated with bending and tension, and then there's a mode 3 contribution that is associated with torsion. And now, how do you want to combine them towards failure? Perhaps through a combined loading criteria that looks like this. Okay.